everyone, thanks for the time. I'm going to walk you through something I built, an infrastructure recommendation engine. So observability tells you what broke, this tells you what to fix with a traceable chain of evidence behind every recommendation. Let me start with the architecture. This covers both what we built and how it works end to end. On the left, you can see it's a simulated infrastructure, Care-Track, a healthcare booking platform on real AWS, Node.js API on K8s, MySQL RDS, 3 Lambda function, and 3 traffic simulator, and a single traffic simulator hitting all 6 routes continuously. The engine collects signals from 2 independent sources. OpenTelemetry traces every API request, which route was called, what SQL ran inside it, how long it took, and Prometheus watches the database independently. Table input output, index usage, row scan counts. When both sources agree something is wrong, that's corroboration, not a single noisy signal. So those signals feed into the recommendation engine, which works in 5 steps. We built the graph. The engine reads live data from MySQL's information schema and OpenTelemetry spans and builds a dependency graph using network X. So it's route to query, query to table, then table to index. This lets it answer why is this route slow by tracing the full chain, not just looking at one metric in isolation. Now in step 2, we build the gates before surfacing anything. The engine applies deterministic rules. The table must have at least 1,000 rows. Latency must exceed 1,000 millisecond for a warning or 5,000 millisecond for flagging something as critical. Now in step 3, and this is where the vector DB comes into picture, the RAG pipeline. So here the Chroma DB, which stores the documents in the embedded form. So we store 3 documents: MySQL 8.0 reference manual, AWS Lambda best practice documents, and K8s documents. So every recommendation's explanation is retrieved from this library. Nothing is made up, and this is our citation story. Now, in step 4, we write everything to a ledger. Every finding goes into a SQLite ledger with full context. What was found, what is the fix, and when it was detected. And in step 4, this ledger is fed to the UI. Fast API reads from the ledger and subs the recommendation to the prototype, what we are about to see. Now, one thing I need to clarify is for compute recommendation, EC2, Lambda, and K8s, the graph is bypassed. Those use direct metric and configuration checks. Different question, maybe simpler answer and more objective answers. So we collect signals, connect them with evidence, filter noise, and recommend a specific fix. Now, on the recommendation engine application, so CareTrack is a healthcare API. So it has doctors, patients, appointments, and clinic dashboards as the routes. So this is a real stack, 6 routes, nearly 50,000 rows in the appointments table. This is small enough for a prototype, but realistic enough to source or to surface some genuine problems. Now route latency view, which is the left panel, this is the route latency view. 5 routes are healthy, nearly 2 milliseconds to 34 milliseconds, but one is not. So the get dashboard clinic, it's 810 traces per minute, and the P95 latency is 174,352 milliseconds, nearly 3 minutes. The clinic admin dashboards is a frequently used dashboard, and I can only imagine that you hit this route on login, on refresh, probably every morning. So this is high frequency and extremely slow. Now on the recommendation panel, um, uh, the engine had surfaced 8 findings: one critical database finding, EC2 memory pressure, and AK8s parts misconfiguration, Lambda memory headroom issues, and unused index. These have passed through the gates first, the deterministic gates. So they are not raw alerts; they are filtered recommendation. Now I will go through the critical finding. So This is the critical finding full table scan on appointments, 50,000 20 rows confirmed live from information schema. Here is the graph traversal in action. So route is get slash dashboard clinic. He hits the query group by date on created at column. So that's a function wrapped in that's a function wrapped column. So we see the complete query by hovering over the SQL statement, and it shows it hits the table appointments with 50,000 20 rows on every request. Then it gets joined to the doctor, which has only 100 rows. And that's where the recommendation on doctor is rejected because it doesn't pass the get and it's not worth surfacing. Now, from these, the root cause is detected. So the root cause is no covering index uncreated at for this access pattern, and from this the fix is also detected. And the fix also suggests that use the SQL command with algorithm equal to in place and lock equal to none. So this comes from our grounding of documents because it's going to be online DDL, which means there will be no downtime. So this is the grounded information that comes from the RAG layer. Now we also provide appearance to copy it, so you can copy it and directly move to the deployment workflow. Now there are other findings which are related to non-graph findings like EC2 memory at 75.3%, and then the Lambda traffic burst 800 MB against 128 MB. Yeah, that's coming from direct CloudWatch check. These are also coming from the citation is also coming from the grounded information that we have in our vector DB. I'll quickly switch over to the integration endpoints. So three natural entry points, I would suggest that one we already have in Neuralink. I think two we already have in Neuralink. It already has the recommendation inside all capabilities, and we are going to surface it here. I have just marked it as a featured uh, recommendation because I want really the discovery to be more and more seamless for the users. So this is the first layer, and then where every recommendation just pops up. Then we have entry points where the engineers are already present. So where, for example, inside APM and services, we have recommendation which is also present, and here we can filter the recommendation which are applicable to this layer. And similarly, we have the database layer where we can show the recommendation. So basically, the integration story goes like you meet the engineers where their data already exists, and you know those are the pages, or those are the uh, sections where engineers spend most of their time. So the recommendations should have multiple entry points. So we need to turn those signals into recommendation where engineer is already there. I'll spend some time on the roadmap and what is already built, and what's how I'm envisioning this to be in future. So what's built today is the telemetry ingest, evidence graph for database recommendation, direct metric checks for compute, and the rack grounded explanation. Now the roadmap is probably something I want to take it one step further and bring human approval before any apply fix. So if I open it, you can see the apply fix is currently disabled. So how I'm envisioning it is this becomes active, and the apply fix is actually the application of the fix, maybe in a simulation traffic, to provide the confidence to the end user that how the metrics is going to change, what is the before after story, and then probably a full loop from here to detect, diagnose, recommend, approve, and apply and prove. Maybe at some point we'll integrate the complete workflow, like you open a Jira ticket and we suggest something as a fix for the ticket and we apply it, then we provide the observation on top of what is applied. So those are the two things, which is human approval and measure proof. And I also think at some point later, the ML becomes genuinely useful once we have more and more data, and the data is really compounding every day. So today it is very deterministic. Engineers need to trust and explain what they act on. Over time, ML learns seasonal patterns, adaptive baselines, where the deterministic gets becomes more and more adaptive depending on the signals that we get from the ML engine, and then we predict the impact. So deterministic reasoning builds the trust first, then ML makes the engine smart over time. So yeah, so that's the walkthrough. Observability tells you what broke, this tells you what to fix with traceable evidence. Thank you so much.